tous. Aujourd'hui, on va accueillir Hiroshi Matano, professeur Matano de l'université Meiji Kyo, qui va nous parler de résultats de convergence pour des systèmes coopératifs avec conservation de la.
Okay, so I would like to thank the organizers of this seminar, Franz Amura and Professor Yves Ashdou and many other things, for giving me this opportunity. And during the COVID-19, I could not come to Paris. And actually, in last December, I made a short stopover in Paris before going to Nancy for 3 days. But this is the time when I'm really staying in Paris for nearly 2 weeks. And I'm very glad to be here. And also to see many people whom I know. And the title of my talk is about some dynamical systems that has order preserving property, plus what could be called a mass conservation. And if you combine order preserving property and mass conservation, you can prove many things just based on these two properties. And I will show some examples later. And the first part of my talk is joint work with Toshiko Ogiwara and Daniel Hilhorst. And the second part, which is on cooperative systems plus mass conservation, this is joint work with Toshiko Ogiwara. This is a continuation of our work with Ogiwara and Daniel. So this is the outline of my talk, and here is the background. And the goal is just, for example, let's consider an evolution equation. Let me just move this away. Evolution equation, for example, as an example, is kind of operator, nonlinear operator, which is either autonomous or time periodic. And suppose that this equation satisfies the comparison principle or order preserving property plus mass conservation. So certain value is preserved. Then one can show the convergence and also many other properties of the structure of the equilibria. And applications include molecular motor model or reversible chemical reaction model or some delay differential equations. And I will talk later about some models in economy. So, roughly speaking, the first part of our result claims that the existence of stationary solutions under certain conditions or time periodic solutions and the convergence to a stationary solution. And this can be shown very, very easily without using the special properties of the equation. All you need to use is the comparison principle plus mass conservation. So let me first explain what is the order preserving property. So I consider order the metric space. So it is the metric space X has a distance function D and order relation. And we assume that the order relation is closed with respect to the limit. So if you have an ordered Banach space, then the positive cone is closed. So this is what this means. But I don't assume the linear structure on X, so X need not be a Banach space. And also I use the notation U strictly larger than B. It implies that U is larger than or equal to B, and they are not identical. And the examples, simple example is Rm, and the order relation is component-wise. This is a typical simple example. And U strictly bigger than B means that at least one component, the strict inequality holds in at least in one component. One can also use this strong inequality like this. It means that for every component, the strict inequality holds. But I don't use this last notation. it is not needed in our topic. So this is the typical situation where U is larger than or equal to V, and the green one, U, is strongly bigger than V. And the red one, U, is bigger than or equal bigger than V, but they are not equal. So the second case, this is the second case. And R1 is a totally ordered set, and Rm is partially ordered with this order relation. Another slightly more interesting example is the space of continuous functions, and the order relation is defined naturally pointwise relation. And this is the case where V is bigger than U, and they are not equal. But the graph can touch somewhere. But if V is strongly bigger than U, then the two graphs don't touch. And another situation in which X is not a linear space is the set of non-negative continuous functions. So this is another typical example of ordered metric space. And also the vector valued the same. And for compact sets in Rn, the order relation is also defined. So the family of compact sets in Rn forms ordered metric space with respect to the Hausdorff distance. So this is the case when space X doesn't have a linear structure. So order preserving definition, order preserving, which I abbreviate as OP, is that, by the way, in this talk, I focused on the map dynamical systems. I started with the example of ODE or PDE, but the results, abstract results, are stated for the map dynamical systems, and you can apply this to continuous time dynamical systems, but the basic results are all given for map dynamical systems. So time discrete models are also covered. This is the order preserving property, and there is also a notion, stronger notion of order preserving property, which is called strongly order preserving. I abbreviate it as SOP, and if it means that if U is strictly smaller than V, then there is neighborhood capital U and capital V of little u and v, such that the image of U is strictly smaller than the image of V. So this is a strongly order preserving property. And this is a very strong property, and from this one can derive many results concerning the stability, and also it says that the internet connections are not stable, this Wi-Fi, but it's okay. So this strongly order preserving property implies that if the graph of V is above the graph of U, and if the two graphs are not identical, then the image of the two graphs completely separated. So this order preserving property alone, strongly order preserving property alone, can produce many interesting results. I started to work on this problem in 1980s, and Maurice Hirsch did it a little earlier, and just by this property one can derive many properties, dynamical properties of the system. However, if you combine this property with mass conservation, much more can be said. And moreover, this strongly order preserving property, this condition can be relaxed, as I will show later. So then there is semi-flow version of the same properties. Semi-flow is order preserving if for each t. This map is order preserving, and the same for strongly order preserving property. Typical examples are some quasi-linear parabolic equation on a bounded domain, or cooperative reaction diffusion systems, or competition reaction diffusion systems of two species and some delay differential equations fall into this category. And a great amount of studies have been made in 1980s, 90s on the dynamics of such systems. Hirsch and myself, Melchinsky, Takac, Hal Smith, and other people. And let me first state first result, which is a joint work with Toshiko Ogiwara and Daniel Hilhorst and DCDS Series 2020. In the abstract, I wrote DCDS Series B, but actually it is Series B. So the basic setting is the following. I don't know how to erase the top. It's a little, this one I want to erase from the, but I hope it's not so bothering you. So, but all my results are stated for the map dynamical systems, and it can easily be carried over to continuous time systems. So the underlying assumption, standing assumption on the map F is that F is compact. F is a map from X to X. F is compact and order compact. Order compact means that if you have an order interval, then its image is very compact. F is order preserving. The F2, the third property F2 is that if U and V cannot be compared, then the image, I forgot to say that there is a least upper bound. For any U and V in X, the least upper bound can be defined, and it's a continuous operation. So max UV is f of max UV is bigger than max FU FV. This means that if U is a continuous function, V also, then max of UV is this red curve, and its image by F is separated. And we call it strictly separating property. And this is weaker than the strongly order preserving property. This is mildly strongly order preserving property. So this is the standing assumption for this first part of the result. And then there is another map, which is the mass in some sense. For every point in X, a value, real number is associated. It is a continuous map. And this is strictly increasing. U strictly smaller than V means that M of U is strictly smaller than M of V. And the second property is that M of F of U is equal to M of U, which means conservation, mass conservation. So basically, these are the only assumptions I assume. There is one additional assumption which I will assume for one particular result, but basically just F and M. So this is very, very simple assumptions. But it turns out that many things can be derived. The first theorem is the convergence theorem. So the assumption is this mildly strong comparison principle plus mass conservation, which I just stated. And the first theorem is a strong theorem, and any orbit is either it converges to a fixed point as n tends to infinity, or it escapes to infinity, which means that distance of F and U from any reference point go to infinity, so it goes to infinity. Either one of the two possibilities hold. And the corollary is that if there is bounded orbit, automatically it means that F has a fixed point. It's an immediate corollary of theorem 1. And another corollary is that I don't go into the details of the proof, but the corollary B is that if B is a fixed point of F to the power M, so this is a composition of F, M times. If B is a fixed point of Fm, then automatically it is a fixed point of F. This you can derive from theorem 1, because, okay, I can say that if B is a fixed point of Fm, then if you consider Fmk, k is an integer, FMKV is equal to V. So the full orbit Fn of V doesn't go to infinity. There is a bounded subsequence. Then by theorem 1, automatically it means that FMV converges to a fixed point, and therefore V itself is a fixed point. Okay, so I just skip it. And so applying this theory to the following periodic problem, periodic evolution equation, then any empty periodic solution of this system is actually T-periodic, provided that A satisfies this order preserving property plus mass conservation. And the second theorem, I assume the following, the additional assumption X, which says that for any X in the space X, for any point little x, there exists a sequence xk converging to X from above. This is the additional assumption. And if X is a Banach space, if it is, it has a linear structure, of course, X is automatically satisfied. And then the second theorem, which is, I think, interesting, says that let E denote the set of all the fixed points of F. If E is not empty, then it is a totally ordered connected set. Furthermore, E has no upper bound, which means that E is necessarily infinite set. So if there is one fixed point, automatically there are infinitely many fixed points. And so the immediate corollary to this theorem states that existence of a trivial solution implies existence of infinitely many non-trivial solutions. For example, if this is a linear problem, then zero is always a solution. Automatically, it implies the existence of a positive non-trivial solution automatically. And then this is the summary. And earlier related results is by, for example, in 1991, and the convergence of Fn and the assumption that there exists a fixed point V with the same mass with U, initial data U. Then he proved convergence. But our results don't need to assume that for the convergence result, we didn't assume the existence of fixed point. It comes automatically. If there is a bounded orbit, automatically there's a fixed point. Mirochinsky and Banerjee and Angeli proved a similar result to ours in Rn, finite dimensional setting, and the additional assumption that M is C1. And they also use the linear structure of the base space N, and also the differentiabilities. So the proof is much more technical and complicated compared with our abstract proof, which is much shorter. And the main result, part 2, is the following. So this is on the general cooperative systems with mass conservation. And this is joint work with Toshiko Giwara. And this is a generalization of the earlier work by Nakajima in 1979 and Jiang in 1996. Nakajima, paper appeared in the Siam Journal of Applied Mathematics or something like that, and Jiang's paper appeared in Siam Journal of Mathematical Analysis. And our result is the generalization of their work to an infinite dimensional setting. So a typical example of cooperative systems, let me see if we can, okay, anyway, I hope it doesn't bother you so much. ODE is a cooperative system, PDE, something like this, and ODE, it is time periodic or autonomous, and PDE the same, where LJ is a second order elliptic operator, so it's a parabolic equation, and therefore it satisfies the comparison principle for each component. And cooperative system implies that derivative fj for each j, fj is non-decreasing with respect to uk if k is not equal to j. So this is the cooperative condition. And many results often assume the cooperative system is order preserving. It is well known. And in order to derive some strong results, usually people assume irreducibility of the system, which means that if you if you write down m by m matrix and see which part, in which component the derivative of fj by uk is positive, it is either 0 or positive. So if you just look at the positive part, and then this positive part from any j to from any I to any j, if you can connect by a path. So you just look at oriented graph of m nodes and just draw a arrow. If ij component is positive, draw an arrow from I to j. Then with this arrow, if you can go from any node and follow the arrow and reach j, if this can be done for any I and j, it's called irreducible. And often the irreducibility is assumed to derive some nice result but here we don't assume any irreducibility, so it can be completely 0 for all j and k. So this is our main point. By the way, it seems that it is freeze. It freezed. Just a second. Oh, now it came back. Now, okay. So goal is to show convergence of orbits, stability, and existence of equilibria of fixed points. And again, here, the results are given in the setting of dynamical systems. So here is the, okay, let me see. Okay, now it's okay. So we consider discrete dynamical system generated by the map F on the space X. But this time the space X is a direct product of m-ordered metric spaces, x1 to xn. And each xj has a property similar to the one I mentioned in the previous section. And distance is just the sum of the distance, of component-wise distance. And order interval is defined by this. And the least upper bound of u and v is defined component-wise. And the map F has a component f1 to fm. And it maps a point in x into x. So this is the assumption. It is a little long, but it's basically similar to the one before. The first one is F is continuous and the compact mapping. Equivalently, it means that each component Fj is compact, and F is order preserving. Just order preserving, not strongly order preserving at this stage. But F2 is a slightly strong property. Fj is strictly increasing. Namely, if the jth component strictly increases, then Fj, the image by Fj strictly increases. So each component of F is strictly increasing with respect to the jth component of U. And F is strongly separating. I wrote that strictly separating in the earlier slide, but it's the same. Let me write down this one once again, this one. And this last property, F3, is this. But I assume this only for each component, Fj, not for the entire F. because I don't assume any irreducibility of the system. Therefore, the entire F may not have this property, only Fj. If you look at this property F3 carefully, then it means that if Uj and Vj are not ordered, neither is smaller or equal to the other, then Fj of max UV is strictly bigger than the max of Fju, Fjv. But if if Xj itself is a totally ordered set, this assumption is meaningless. For example, if Xj is, then this assumption is meaningless. So F3 is automatically satisfied if each Xj is a real number, the set of real numbers R. And in particular, if we apply it to finite dimensional systems, we can forget F3 because it's automatically satisfied. And in that case, all we need is F0 to F2. And it's a very, very mild assumption. And then we also assume the existence of mass is a continuous function on X, and the same as before. M1 is the same as before, strictly increasing, and M2 is milder than before. M2 prime is the same as before, mass conservation. And actually, most of the results which I state here holds under the weaker assumption M2. But let's focus on M2 prime, which is the same as before, mass conservation. Then we have the following theorems. Under these weak assumptions, we can show that any orbit Fn either converges to a fixed point or escapes to infinity. This is the same as theorem 1. And the stability, assume M2 prime, so mass conservation, then any bounded orbit is stable in the sense of Lyapunov. And the corollary, immediate corollary of theorem 3 is that if there is a bounded orbit, then F has a fixed point. This is the immediate corollary. And the immediate corollary of theorem 4 is that any fixed point is stable. And also, if we assume that any point in X is not isolated from above, which is satisfied if X is a Barnard space, for example, then if there is a fixed point, then there are infinitely many fixed points. So it is similar to the structure theorem, which I stated before in theorem 2. So these are the results, and they all follow from the assumptions I stated. So the proof is completely abstract and moreover very simple. We don't use very complicated properties of the space. Sketch of the proof, but let me go very quickly just to finish it. So the first lemma is that if the omega limit set, this is for the result 1, but the main for theorem 1. If the omega limit set is not empty, then it is a singleton. It means that the orbit converges. So this is the main point of the convergence theorem. But how do we prove it? And it is actually surprisingly simple. Just a second. Okay. And by mass conservation, along the orbit is constant, and therefore, for any omega limit point W, omega limit point of U, the mass is the same as the mass of U, which I call alpha. So by the strict monotonicity of M, distinct points in omega U unordered. This one can show. There is no such, okay. Unordered means that no omega limit point B is smaller than omega limit point of U, or this kind of relation doesn't happen because otherwise by the strict monotonicity of M, the value is different. So any omega limit points are not ordered. So suppose that omega u is not a singleton, and we consider this value. Since omega limit set is, okay, I assume that the orbit is bounded at this stage, then it is compact. Then there is such a maximum of this because m is continuous function. So this has maximum value. And beta is strictly bigger than alpha, since if v and w in the omega limit point, and if they are different, then max vw is strictly bigger than v, and therefore this is strictly bigger than alpha. And the beta is bigger than or equal to this, so beta is bigger than alpha. And suppose that v1 and w1 are the points which attains this maximum. Clearly, v1 is not equal to w1. And since omega u is an invariant, its omega limit set is an invariant set, there is a pre-image of these 2 points, which I denote by v0 and w0. The points v0, w0 again distinct. Therefore, they are distinct because if they are the same, they cannot be the pre-image of different points. And therefore they are unordered. So f of u0, max u0 v0 is bigger than max of f v0, f w0. And therefore, if we look at the mass of these points, this is bigger than this by the monotonicity of mass. However, since the mass is conserved, the m of f max v0 w0 is equal to m of v0 max v0 w0, and this is of v1 max v1 w1. And this is a contradiction because of v1 w1 is the maximum, and of max v0 w0 is bigger than the maximum. This is a contradiction. So this contradiction came from the fact that omega u is not a singleton. Okay, so from this follows theorem 2, convergence. Okay, let me just skip some many points. And okay, I think I had better skip these the proof of these other theorems and corollaries. But in any case, as you see, the argument is rather simple, very simple. But the important thing is that many nice properties follow from this. And here is application, for example. One is a molecular motor model, which is like this, and it has been studied by Shippo, Hastings, Kindler, and this kind of system. And it tries to explain how the muscle move, and the flashing ratchet models and the flashing ratchet systems. But let me just skip the details. But then about this model, there are some talk about a convergence to a stationary solution, relative entropy method by these people, and the existence of stationary solutions are given by Shippo, Hilhorst, Kindler, Olek by using Klein-Rutman theorem. And also there are other people working on that. However, convergence and existence of stationary solution follows immediately from the abstract result which I mentioned, because it's a linear system and zero is the solution. Therefore, automatically there exists positive non-trivial solution automatically, and moreover, any bounded orbit converges to a stationary point. So we don't really need to use these elaborate analytical method. All we need is to just apply this simple abstract theorem. And another one is reversible chemical reaction model. And this has nonlinearity of the same type, where alpha and beta are positive constants. And then it has mass conservation. This one is a constant. And Bote and Hilhorst, for example, proved the convergence of solutions by using the L1 contraction property of this system. But we don't need to use L1 contraction. Our results applies to this system, and also we can generalize their result to time periodic cases, because our results stated for map dynamical systems, therefore it applies to time periodic systems. And there are cooperative diffusion equations. And okay, let me just skip all these, I'm sorry. And then application to modeling. Suppose that there are M commodities that are labeled from 1 to M, and the P of T denotes the price at time T of each commodity, P1T to P1 PMT. And XJP is the demand for commodity J if the price system is P1 to PM. So the demand for each commodity is a function of the price system P. So this is the assumption. Then the important question in the market economy is whether or not the price converges to equilibrium state, equilibrium, in a short time, so that market is in equilibrium. It's not long-term development, but convergence to the equilibrium price in a short time. Then what is called the Tatonement process in economy is a system of ODE like this, where xj bar is the equilibrium point. So it means this. So if for each j, xj p1 to pm is equal to xj bar, then it is in the equilibrium state. In economics, there is this identity. It is called the Walras law. It is this. And the gross substitutability is this property. What does it mean? It means that the demand for xj increases if the price of other commodity increases. So if the price of other commodity increases other than J, then the demand for the commodity J increases. Usually they use strong inequality, but one can relax this condition to inequality with equal sign. Then one can show in economics books, they prove the convergence by constructing a Lyapunov function for this. But it turns out that using our theory, one can prove the convergence not by constructing a Lyapunov function, but by just applying directly our method, because we have mass conservation coming from Walras law, and gross substitutability in a weaker sense is a comparison principle, and each component is R, so it's a real valued, so automatically all the assumptions are satisfied. But possibly one can generalize this into the case where the price is not necessarily a real value, but some sort of functions. And I don't know, I don't have a particular good model in economics, but our theory can apply this Tatonement system if the price is generalized to functions. But I don't know if this makes sense. So I think this is the concluding remarks, and there are many open questions, but since my time has come, I would like to finish my talk. But what I wanted to say is that many nice dynamical properties of such a system can be shown by a rather simple abstract results. And I think there are possibly many other applications. And if you have other ideas for applying this theory, I will be happy to listen to you. Thank you very much for your attention.
Thank you. Very good question.
Yes.
First of all, I am surprised by the result that if you have a fixed point, they are all stable.
Oh, yes. They are all stable, but none of them is asymptotically stable, of course. If none of them is asymptotically stable, if you perturb the mass of the initial data, it converts to different equilibrium point with different mass, of course. But if you keep the same mass with a perturbation, in that sense, it's asymptotically stable, yes. Yeah, but otherwise, it's only stable in the Lyapunov, in the sense of Lyapunov. Yeah.
Go back to the difference between the part 1 and part 2.
Yes, yes. Part, okay, part 2 is in some sense extension part 1. So it turned out, okay, I wanted to, okay, let me just tell you. We had the result actually with Daniel Hiroshi, who is here, and also Toshiko Gibara. Part 1 result, which tried to prove many known results or improving it by a simple general theory. However, we realized that Nakajima in 1979 and Jian 1996 worked on an ODE system, cooperative system, in which they didn't assume any irreducibility. And our slightly stronger version of comparison principles still needed to assume some sort of irreducibility in a weak sense. So we tried to think what is missing in our argument. Then we realized that cooperative systems, ODE or PDE, are well-known examples of order-preserving systems. They satisfy comparison principle. However, it is not a general type of order-preserving system, but it has a special structure. It has a vector component, and each function has this property. And in our part 1 result, we stated everything in an abstract way and did not use the fact that it's a cooperative system. And the cooperative system is a special class of order-preserving systems, and we realized that this is the point. And then we realized that we can extend the results of Jian and Nakajima to infinite dimensional setting by looking at space, which is a product of spaces, and the function, the map F also has M components, and it applies to each component. So it has a special structure, and using this structure, our proof is different from Jian or Nakajima because we work on the discrete system. They work on the ODE with time periodic ODEs. So argument is simpler, but we wanted to use this structure, which is a special class of order-preserving semiflows, and we managed finally to prove what we wanted. And the only assumption we assumed is that for each component, Fj has a strongly separating property as in the first part. But the combination of F1 to Fm needs not satisfy this strong separating property, only for each component. And so each component, if it is a real number, it's totally ordered set. So strongly separating property is meaningless. We don't need to assume it. So for ODE, the F3 is not really needed, but for more general infinite dimensional system, we need F3. So we say that the first part result is the case where M equals 1. And we extend it to a general M, but without any irreducibility conditions. And so it applies to, I think it increased applicability of our general result. Yeah.
Maybe just to what you have said, but for me in the old time of studying or teaching the ordered space that was really related to the Perron-Frobenius theorem or the dimension, which is the Klein-Rootman. And the example I had in mind, Klein-Rootman said that the result was that there was only one stable state. Now, can you elaborate on the example where you raised the issue of Klein-Rootman? What is the difference of what you get? And where is the difference between the situation where you have one stable state and where you have an infinite set?
No, it is completely, Klein-Rootman is a special case of our theorem. It's a linear problem. Linear problem, therefore, if you have one...
How more general is...
So, one unique eigenvalue and the positive eigenfunction implies that multiple of this by any positive number is again a fixed point. In that sense, Klein-Rootman doesn't say that the eigenfunction is unique. It's unique up to multiplication of constant. And so it completely agrees with ours, and the Klein-Rootman theorem follows from our theory, actually. Yes, so it is related. But unfortunately, our theory only deal with the case where there is a mass conservation. And if you don't assume mass conservation, then the existence of a positive eigenfunction, you need to require some more argument. But if you use mass conservation, all the proofs becomes much simpler. This is the point of my talk, yes.
Any question? I will ask if there is a question in the audience online. It seems that there is no question, so we thank you very much.
Okay,